We start our introduction to the second half of what calculus is about. We have spent the first half of the year on differential calculus. Differential calculus, all right, is the idea of a derivative. Okay, these are all, differential calculus is all about derivatives. And if you remember, we learned about the difference quotient, right? We learned about the limit as h approaches 0 of f of x plus h minus f of x all over h. We learned about that thing. We spent a lot of time working with that, and we found out that this is the definition of derivative, f prime of x. We spent a lot of time there, and it's a skill that we still have to have very good or very solid. We called these derivatives a bunch of things. Didn't we call it the slope of the tangent line? We said the derivative can tell me the slope of the tangent line. What else? What other phrases did we use? Yes, very good. The instantaneous rate of change. I heard another one out there. Velocity. Okay? Velocity is the derivative of position. All right? That's very important as we head into the second half. I heard somebody say that the derivative is the general slope function. Okay? It is a function that can tell me the slope of the tangent line anywhere I want. Okay? So all of those things are true. All right? But when we talk about integral calculus, all right, when we talk about integral calculus, instead of being concerned with, I'm going to come up here in the corner, you know, if I've got my little function up here, with integral calculus, I'm wondering, okay, what's the slope of the tangent line right there? Okay? That's what I'm concerned with differential calculus. With integral calculus, if I've got some function, all right, let's say that's my pretty little function, instead of being concerned with what's the slope of the tangent line at a certain instant, I'm going to look at an interval, like from A to B, and I'm going to be finding out the area between the curve and the x-axis. Now sometimes we'll do it in relation to the y-axis, but we're going to start out learning how to do it with the x-axis. It's the idea of the area under the curve. Area under the curve. That's the idea with an integral. Okay, we have to have, you know, a correlation to something that is real and finite, and that's what it is. It's the area under a curve. So let's kind of look at a very simple example of how this could play out. Let's say that we've got a train going 75 miles per hour, and this is a constant speed. It's never changing. All right, this is constant. All right, a constant speed. And then let's say that we have this little question. How far did it travel from 7 a.m. to 9 a.m.? Now don't shout out answers yet, because we're going to look at this graphically. Okay? So let's kind of draw a little graph here. And if you remember, which one of these two axes is velocity? This one. Yes, this is velocity. And then what's the x-axis if we're talking about velocity? It's time. All right? So if the train is going 75 miles per hour at a constant rate, aren't constant functions flat? Aren't they horizontal? I would have a flat function. Okay, that is its velocity. Okay, this would be what we call the velocity function. And in this case, it's just a constant. But we said, okay, how far did this train go from 7 a.m., 1, 2, 3, 4, 5, 6, 7 a.m. to 9 a.m.? Now, I think we all know how to answer this question without the graph. Isn't it 2 times 75? But look, if I make this a rectangle, and I look for the area between that constant function and the x-axis, or the time axis, the length is 75. What's the width? 2. What's 2 times 75? 150. Okay. So, in other words, finding this area tells me how far it traveled. Okay? Finding the area, let's make a note of that. Note. Finding the area tells me how far it traveled. Okay, very important idea. So, now this was nice and neat and clean because I had a constant function. But what if the train's speed was not constant? What if it was all over the place? Like the Polar Express. What was that big gulch, or when it went down the great big hill? It said, we're coming up on something gulch, and it's the steepest incline in the whole world, right? So obviously when you're going up the hill, your velocity slows down, right? And when you're going down the hill, when I'm coming up the hill, if this is velocity, if this is v of t, when I'm going up the hill, when I'm going up the mountain, my velocity goes down, and then as I start going down, like on a roller coaster, the velocity takes off. Well, didn't I just find that distance traveled? If this was 7 a.m., and this was 9 a.m., and I wanted to find the area under that, well, I've got a problem. Because I don't have a nice square rectangle. But if I look at a little tiny rectangle, and maybe I make another little tiny rectangle, and I make another little tiny rectangle, and I make another little tiny rectangle, all of a sudden, if you look up here at the top, okay, it looks a lot more square at the top if I use a little tiny rectangle. And if I let me get a different color. If I let the number of rectangles approach infinity, and then add them all up, okay, if I let the number of rectangles approach infinity and then add them all up, I could do it. And that was one of the great discoveries that Sir Isaac Newton came up with when he discovered the calculus. He said, if I let the number of rectangles go to infinity and add them all up, I could do this. Because if I have an infinitely small rectangle, then it starts to approach being a square rectangle. Okay? And that's what Sir Isaac Newton did. All right? So let's get into an example. Let's start learning. This is kind of called, at the beginning, we're just forming a foundation for integrals. And we are going to do some estimating with finite sums. We're going to do some estimating with finite. What does finite mean?
Not infinite.
It's not infinite. That's a good statement. Isn't it something that we can know?
Yeah.
Right? If it's finite, it's got a limit, and there's something we can know about it. So here's our example. Yeah, finite means it's something we can know. Okay? It is another phrase could be it has a limit, or there is, infinite, there's no limit. If it's finite, it's got an ending. Okay? That's probably it. Finite is related to the word finish. So it's got an ending. A particle starts at x equals 0 and moves along the x-axis. This is going to look incredibly familiar. Moves along the x-axis with velocity v of t equals t squared for t greater than or equal to 0. Where is the particle at t equals 3? Now notice something. We weren't given the position function, were we?
No.
We weren't given the position function. We were given the velocity function. And you actually have seen some of these problems show up, and I told you we would learn how to do it later. This time we were given the velocity function. And let's go back. Let's review where we just came from. Didn't we calculate how far the train went from a velocity function right here? Right? I knew the velocity, I knew the time, right? I just found an area under the curve. So on this problem, we're going to do the same thing. I need to find an area under what curve though? The curve is t squared. It's a quadratic. So what we're going to do, and make sure you draw this graph big, okay? Draw this nice and big on your paper. My function is t squared, which is a quadratic. And we're only concerned with positive time values, all right? And we said, where is this particle at t equals 3? So let's say that 3 is over here. Okay, and so we'll divide this up into thirds, 1, 1, and 2. Okay. Well, unfortunately, my velocity function is changing. It's not a constant. So what we're going to do is we are going to break this into some rectangles, and we're going to didn't I say that this was estimating? See this word right here? That's very important. We are going to estimate the area under the curve. Okay? And how are we going to do that? Well, we're going to break each of these intervals up into fourths, like this. We're going to break it up into fourths. And then within each of those fourths, okay, we are going to go halfway in between. So let's say I were to use this one right here. Halfway in between, and that point is going to be the midpoint of a rectangle that I draw. Like that. And I'm going to do that for all of these intervals. I'm going to come up here, draw a rectangle, bring it down to that point. Put it up there, draw a rectangle, come down to that point. Come halfway, just like that. So my intervals here, this is 2 and a fourth, this is 2 and a half, this is 2 and 3/4, and that's 3. So the midpoint, just to kind of explain a little bit further, the midpoint is telling me where this rectangle is going through on the function, okay? And I'm going to do that all the way across, okay? I'm going to have all these midpoints here.
What did you say about the midpoint?
All of these midpoints are telling me basically how to find the length of the rectangle.
Where the function is that in the function?
Yeah, if I look at my midpoint, okay, let me get a different color here. Let's just take this midpoint right here. If I put in the function value, okay, whatever that is, this would be, what, 2 1/8? I put it into the function, it's going to give me a value, and that's going to be the length of this rectangle. The width of the rectangle is going to be 1/4. Okay? So every rectangle has a width of 1/4. Every rectangle up here is going to be 1/4 units wide. Okay? Every one is going to be 1/4 units wide. But every rectangle is going to have a length that depends on what the function's doing right there. So we've got all these little rectangles. Okay? And what we're going to do is we're going to find the area of each little rectangle. Okay? And we can do this. Now look, let's look at this rectangle. Let's come over here to the right-hand side. Let me get purple or something. Look at this last rectangle. Do you see that this is going to be a little bit of an overestimate because of that in there? Right? That's okay. We're just estimating. All right? We're estimating. And do you see that if I made my intervals smaller, that it wouldn't be off as much? The more intervals I use, the more accurate my area would be. All right? But we're just, because this gets kind of crazy, we're just going to use ones that are 1/4 of a unit long. So let's look at this very first one. I said that this was 1/4, then 1/2, then 3/4. And I said we were going to use this midpoint. So what's the midpoint between 0 and 1/4? Isn't it 1/8? Right? So the width of this rectangle, okay, the width is going to be 1/4. The length of the rectangle, the length of every one of these rectangles is going to be the function value at that midpoint. It's going to be f of 1/8. Okay, because remember, the height of the rectangle is my length. So my function was t squared, so 1/8 squared is 1/64. That is the length of the rectangle. Okay? This is the length, this is the width. How do I find the area of any rectangle? Length times width. So the area of this first rectangle would be 1/4 times 1/64, which is 1/256.
So you just use where the midpoint is?
Yeah, the midpoint value, okay, I plug that into the function to get my length. Okay? So what would I do at the next one? I'll use red. What would this next midpoint be in between 1/4 and 1/2? 3/8. So for this one, okay, the length would be equal to f of 3/8. The next rectangle, I'm moving over one. The length would be f of 3/8. So my function is t squared, so that's going to be 3/8 squared, which is 9/64. Okay? What is the width of this same rectangle, though? Isn't it still 1/4? So now, area equals length times width. I'm going to multiply 9/64 times that same width, which is 1/4. All right? So what I get is 9/256. So look what I've got. I have my first two areas. 1/256 and 9/256. And we would need to do that to all the rectangles. Okay? So obviously, organizing your work would be important, right? So it might work better to do this, to make a little chart. Midpoint value, width, and length, and make yourself a little chart, and then down here we'll have the area. Okay? Now, before I go any farther, how many rectangles would I have? That's important here. How many rectangles would I have on this particular example? 12. Okay? So I would have 12 rectangles. All right? So I would need 12 boxes. My first midpoint value was 1/8. What is the width on every rectangle? 1/4. Every width for every rectangle is the same. Every single one of them is 1/4 all the way across. The width of every rectangle is 1/4. But the length changes based on what the function does. And we've already found that out. We said at this first one that the length of the first one was 1/8 quantity squared. We plugged the midpoint value in and we squared and we got 1/64. So this first one was 1/64. Then for the area, we did length times width, and we got 1/256 was the area of our first little rectangle. All right? The next midpoint value for the next rectangle was 3/8. The width is still 1/4, but my length, I have to square the 3/8. I have to put it into the function. So this was 9/64. So then I do length times width, and I get 9/256. Let's just do one more. Let's do one more rectangle. What would the next midpoint value be? Wouldn't it be 5/8? Okay, so 5/8. And then we're putting it into the function. Remember, v of t is t squared. So I need to square the midpoint value to get the length, so that will be 25/64. So the next area is 25/64. I mean, 25/256, sorry. 25/256. Now, we said there's going to be 12 of them, right? Now, the more important thing I want you to get right now is, what is the total area going to be? When I get all those values, what's the total area going to be? Well, don't I have to add them all up? Right? The total area is going to be 1/256 plus 9/256 plus 25/256, right? Plus all the other ones clear up to region 12, or rectangle 12, right? I'm going to save you a little bit of work and tell you what that total is. Okay? The total area, when I add all 12 of these up, is 2,300 over 256. Now somebody divide that out on the calculator for me. 2,300 divided by 256? 8.98. This is 8.98. I need a new screen. Okay? If the total area is 8.98, what was my question asking? Didn't it ask how far the particle moved? It moved 8.98 units. Okay? This is my answer. The particle, yes, it is approximately. The particle moved approximately 8.98 units to the right. Okay? Pretty exciting, isn't it? Yes, it is. Now that method that we just used has a name. The name of the method we used is called the midpoint rectangle. This is really long, so we're only going to write it once. Approximation method. And guess what? There's a shorter way we can write that. There's a shorter way we can write that. We're going to label this as LRAM. LRAM. Now that's using the midpoint rectangle approximation method. There are two other ways that we can do it. Because remember, let's go back to my picture. I decided on every one of these to make the midpoint be my length, or the function value of the midpoint. I could, let me draw a new picture here. Instead of using the midpoint, let's say these were my intervals. Instead of using the midpoint, I could use the edge of the interval. You are correct. If I was using the left edge on every one, I would be underestimating every time. If it was t squared, right? If it was a parabola, because functions can look different. Do you see that I'm using the left point? Right? The left edge of the interval, right? If I'm using the left edge of the interval to get my length, that is called, this would be LRAM for left rectangle approximation method. And what is the only thing that you would do differently? What's the only thing different from midpoint?
You just use the left corner.
Instead of using the midpoint value, like if these were fourths again, like if this was, let's say that this was 2, and this was 1 3/4, and this was 1 1/2. When I found my length, my lengths would come from these. It would be f of 1 1/2 instead of using a midpoint. All right? That's the only thing you would do differently. Everything else is the same. Now, what do you think is coming next? If we have LRAM, we also have RRAM. So if I have a function like this, and I bring this up and use the right edge, in the case of a quadratic, it would be an overestimate. And I would use the right edge of my interval. That would be called RRAM. The right edge, right rectangle approximation method. Okay, that would be called RRAM. All right? And tonight, you are going to get some practice working with this estimating with finite sums method. And we are going to stop there for today.